Do we live in a giant void that could solve the mystery of the expanding universe? Before answering this question, it's important to note that most theorists and astronomers are convinced that the universe is expanding. The so-called Hubble constant precisely determines how quickly cosmic objects move away from each other, but it doesn't always match real observations. A new analysis of nearby supernovae suggests that this discrepancy might be due to the peculiar behavior of our part of the universe. It's possible we live in a huge cosmic bubble with low density, which distorts our calculations, but according to the prevailing standard model, this shouldn't be the case. Almost a century has passed since scientists first got hints of the expanding universe. Today, this continuous expansion is the main evidence for the Big Bang. Since then, the light from that ancient event has stretched to longer wavelengths, but studying the cosmic microwave background has allowed Edwin Hubble and subsequent astronomers to calculate the rate of the universe's expansion. The accepted value is 70 kilometers per second per megaparsec, or 3.26 million light-years. Thus, for every million light-years, a galaxy or other object moves 22 kilometers per second faster. In most cases, this constant is accurate, but various cosmic anomalies have led to disagreements in astronomy. The fact is that when measuring the expansion rate using local galaxies and supernovae, this value turns out to be about 10% overestimated. Observations have shown that the Milky Way is located in a huge void where the matter density is lower than in the surrounding universe. This could explain why expansion around us happens faster. But there is a serious problem with this hypothesis. The standard model does not account for a low-density bubble in space, though all this is based on the theory of gravity proposed by Einstein. Since then, we've learned a lot about the universe that the renowned scientists didn't know. The research explains the existence of the void using modified Newtonian dynamics, MOND, a theoretical model proposed in the 1980s as an alternative to dark matter. In MOND, there are small changes in Newtonian gravitational calculations, mainly at very low accelerations. Using signals from nearby supernovae, researchers confirmed that this change completely eliminates the conflicting readings, eliminating the Hubble discrepancy. Of course, this is not a proven fact. It's just one of several proposed solutions to the Hubble problem, which other researchers will need to analyze. Another part of the scientific community suggests that this faster local expansion may be the same everywhere, or they simply cannot measure all the dimensions of the universe accurately enough to know the validity of the standard model. The best way to know for sure is to extend general relativity to scales greater than 1,000,000 light-years. But we currently don't have the capability to measure gravity without a gravitationally bound object of the same scale. If we assume that relativity is not constant, it could lead to new disagreements, as with Hubble. However, let's return to the rate of expansion of the universe. Generally, the expansion rate is described by the Hubble constant, but different measurement methods yield different results. In short, the Hubble constant determines how quickly other galaxies are moving away from us, supposedly showing the speed of the universe's expansion. For example, using supernovae or analyzing the cosmic microwave background, the data comes out similar, namely 264,000 and 244,000 kilometers per megaparsec, respectively. The new theory suggests that the universe is expanding faster in the vicinity of about 3 billion light-years away from us. The standard cosmological model simply does not provide for this. In simple terms, researchers claim that Earth could be located in a relatively empty region of space. Inside the void, there's less matter than outside. This explains the deviation in the value of the Hubble constant. So, according to observational data and calculations, near our galaxy, the universe is expanding about 10% faster than farther away. This is true for distances up to 3 billion light-years from Earth. If our value of the Hubble constant is correct for the entire universe, then the universe should be younger. But this contradicts estimates of the ages of the earliest stars and galaxies that we can observe. Another feature of our surroundings that cannot be explained using the standard cosmological model is the void KBC, a huge and relatively empty area of space where the local group of galaxies, including the Milky Way, is located. The existence of the void KBC is confirmed by observations in optical, infrared, X-ray, and radio ranges. Overall, The void KBC is an enormous comparatively empty area of space, containing the Milky Way itself and much of the Laniakea supercluster. This void is approximately spherical, about 2 billion light-years in diameter, with the Milky Way located within a few hundred million light-years of its center. It's fascinating how much there is still to learn and explore, right? This is the largest supervoid known to science. It significantly surpasses the size of the Eridanus supervoid and even the giant void. It is believed that the existence of such voids is consistent with the standard cosmological model. Using the void KBC, the discrepancy between measurements of the Hubble constant using galactic supernovae and Cepheid variable stars and data from the cosmic microwave background and baryon acoustic oscillations has been explained. Galaxies inside the void experience gravitational attraction from matter outside the void, which gives a more local value for the Hubble constant. According to calculations, the density of matter in it is approximately half that in the average universe. Therefore, theoretically, matter in this void bubble should move toward areas with more matter. Earlier, researchers suggested that the movement of matter in our void or emptiness might explain the Hubble tension. In 2020, authors of a new study calculated that due to the influence of the void, the Hubble constant estimate in the vicinity of the Milky Way should be about 11% higher than in the rest of the universe. In the new work, void models were recalculated and results compared with the latest analysis of data from the largest catalog, which contains the most accurate distances to 56,000 galaxies. Calculations were confirmed and matched observations. It was concluded that many inconsistencies in the standard cosmological model with observations can be resolved if it is assumed that the universe loses its homogeneity faster than the model predicts. And this is why voids like the void KBC arise. For the same reason, it is likely that the first galaxies formed so quickly after the Big Bang. Although the authors solve the Hubble constant issue, they do so at the cost of rejecting the standard cosmological model, as it does not allow the universe to be as inhomogeneous as the calculations show. Therefore, as an alternative to the standard model, researchers suggested considering modified Newtonian dynamics, MOND, which we discussed earlier. This hypothesis is indeed compatible with large inhomogeneities in the universe. However, recent work on binary star systems seems to have closed the possibility of using MOND in astrophysics. This means that the idea still requires a new cosmological model of the universe. The universe is truly unique. Aries is one of the most recognizable constellations in both the northern and southern hemispheres. 8 bright stars outline the hunter Aries from ancient Greek mythology. The section of the sky is rich in nebulae and areas of active star formation. Aries is the brightest constellation not only in the winter sky but also in the entire sky of the Earth. Moreover, all its main stars form a strikingly symmetrical figure, so human-like that it's easy to remember this constellation. Let's take a closer look at its stellar pattern. 3 bright stars almost in a straight line and at equal distances from each other play a central role in Aries. This is Aries' belt, serving as a sort of axis of symmetry for the other stars in Aries. The belt stars have Arabic names, Alnitak, Alnilam, and Mintaka. 2 of Aries' brightest stars, Betelgeuse and Rigel, are almost the same distance from the belt. Betelgeuse is at the top left, Rigel at the bottom right. Betelgeuse marks the left shoulder of Orion, while Rigel marks the hunter's right foot. On the right shoulder sits the star Bellatrix, and the left knee is marked by the star Saiph. All the brightest stars of Orion are large, young, hot stars, each emitting tens and hundreds of thousands of times more light than the Sun. The exception is the cold giant star Betelgeuse, which, although young compared to the Sun, is at the end of its evolutionary life path and is a red supergiant. To the right of the star Bellatrix, along the figure of the hero, descends another chain of rather weak stars, among which 3 stars stand out. This asterism is called Orion's shield. Just below Orion's belt, 3 faint stars are vaguely visible, arranged vertically very close to each other. This section of the sky is called Orion's sword. So, our galaxy, like its neighbors, is being pulled towards a certain region of space about 150 million light-years away. And here's the surprise, We don't know exactly what's there, although the name of this mysterious anomaly has already been coined, which makes it easier. Yes, we are talking about the Great Attractor, and it is so mysterious because it is located in a part of the sky called the zone of avoidance, in the direction of the center of our galaxy. There is so much gas and dust there that it is not very visible in the visible spectrum. The problem was solved by studying clusters in the zone of avoidance. To study hard-to-reach regions, X-ray radiation was used, which easily overcomes clouds of gas and dust. Galaxy clusters are sources of X-ray radiation, which makes observation and study easier. In fact, the zone of avoidance is now quite well studied. Galactic gas and dust are also well penetrated by radio waves and infrared light. According to the latest research results, fewer massive galaxy clusters were found in the area of the supposed location of the Great Attractor than expected. Nevertheless, the gravitational anomaly near the center of the Great Attractor, the Abell 3627 cluster, was strong enough to tear apart the spiral galaxy ESO 137-001, also known as the Medusa in the constellation Triangulum Australe. Further investigation of the zone of avoidance revealed that the Great Attractor is a large supercluster of galaxies called the Norma cluster. Its mass is about 1,000 trillion solar masses, or 1,000 galaxies. And although the Norma cluster is huge and local galaxies are attracted to it, it cannot fully explain the movement of local galaxies. The mass of the Great Attractor is not enough to create such an attraction. A study was conducted that calculated that the contribution to the local group's motion from the Great Attractor is only 44%. The rest is related to a global flow, where a significant area of the local universe, including the Great Attractor itself, is moving towards another object. Continuing the research, an even more massive galaxy cluster was discovered more than 600 million light-years from the Milky Way, far beyond the Great Attractor. This is the Shapley supercluster. It contains more than 8,000 galaxies, and its mass is over 10 million billion solar masses, which is 10 times more than the Norma cluster in the Great Attractor region. The Shapley supercluster is the most massive supercluster of galaxies among the 220 known superclusters in the observable universe. And most likely, upon reaching the Great Attractor, the Milky Way, along with the entire local group, will move further towards a more massive object, namely the Shapley supercluster. As usual, a logical question arises. What will happen to Earth? What awaits humanity? But rest assured, there are more immediate concerns to focus on. After all, no one really knows what this could mean or if our planet is in danger. Astronomers say it will take several more years, maybe even a decade, to learn more about this anomaly. Some experts do not consider it a threat, while others claim that all galaxies and clusters are merging into increasingly larger superclusters, leading the universe to its logical end, the Big Crunch, which theoretically could follow the expansion after the Big Bang. However, there's no need to worry. Even if the Great Attractor or the Shapley supercluster poses no dangers, we face issues like climate change, the possibility of a giant asteroid collision with Earth, or a supervolcano eruption causing a volcanic winter, alien invasions, or a madman with a red button. There could be many scenarios. But that's not our focus today. In conclusion, we can note that the Great Attractor is a gravitational anomaly located in intergalactic space. It is essentially a collection of many galaxies, formed and hidden far away. Its large mass, as a result, causes greater attraction of other objects, including us. What do you think about the Great Attractor? And what are your hopes for discovering something new in this area of space, which our little planet is moving towards so rapidly? The birth of stars is a unique and fascinating process, but it doesn't happen in an instant. The transformation of a molecular cloud into a star takes time and, importantly, the right conditions. These dense regions with stars inside appear as dark silhouettes against the rest of the ionized nebula. Such formations are known as Bok globules, named after the astronomer Bart Bok. Back in 1947, the researcher hypothesized that these clouds were like insect cocoons, and he was not wrong. Decades later, we now know that Bok globules are dense clusters of cold gas and dust living in the interstellar medium. Hiding in the shadows of massive molecular clouds, these seemingly harmless and isolated formations play a key role in star formation. Yes, inside these dark cocoons, tiny gravitational inhomogeneities gradually accumulate matter, increasing their mass and gravitational pull. Over time, particles of matter combine into dense cores, compressing under their own gravity. As the infallible force of gravity compresses the matter, resulting in increased temperature and pressure at the core's center, a nuclear chain reaction begins. This explosive phenomenon, known as nuclear fusion, releases an astounding amount of energy and marks the birth of a new star. Today, we know that Bach globules are among the coldest gas formations, with temperatures determined by the radio emission of molecules averaging no more than -250 degrees Celsius. The main mass of gas consists of a mixture of molecular hydrogen and helium. The concentration of atoms and molecules in these formations is higher than in ordinary interstellar gas clouds. It increases towards the center and averages several thousand molecules per cubic centimeter. The mass of dust is about 100 times less than the mass of gas, but it is the dust that provides the opacity of the globules, making them visible as dark spots. Thanks to the low temperature in the most massive globules, the process of gravitational condensation of matter becomes possible, leading to star formation. This is confirmed by the discovery of infrared radiation sources within the formation. The appearance of infrared sources is associated with the heating of dust by the radiation of one or several newly born stars, whose visible light does not penetrate through the thickness of the dust. The high density is justified by the fact that substances like carbon and hydrogen, under the influence of low temperatures, begin to combine into molecules from individual atoms. Thus, the merging into molecules of denser matter is the reason for the high density. These cosmic clouds are almost completely dark and unattractive even to the most modern optical instruments, which is their most well-known characteristic feature. To date, at least 349 dark nebulae have been discovered. The most famous examples are the Horsehead Nebula, the Coal Sack, the Snake, fragments of the Eagle Nebula, and the molecular cloud Barnard 68. Most globules were discovered and studied by astronomers using modern telescopes, particularly the Hubble Space Telescope. Let's take a closer look at some of them, such as detailed images of the IC 2944 region or the running chicken. Where it is running and why is truly unknown. The mysterious region is located in the constellation Centaurus, about 6,000 light-years away. Here we observe dense opaque dust clouds that stand out clearly against the background of bright stars. They are filled with gas and dust, which is illuminated and heated by the radiation of stars in the Era cluster. These stars are much hotter and more massive than our Sun. In the constellation Cepheus, located about 2,000 light-years from us in the emission nebula IC 1396, the globule had an even more unusual shape. Its visible size is more than 10 times the diameter of the full moon. Among the intriguing dark figures in this area, the Elephant Trunk Nebula looks not only unusual but even sinister. However, the only real monster here is a bright, young, and rather aggressive star. The high-energy light emitted by this star separates the dust in the dark, comet-like region. Streams of particles ejected by this star also push away the surrounding gas and dust. And in the entire emission nebula, there are many other smaller, irregularly shaped globules that are likely to be destroyed over time. Let's consider the next cosmic formation. This is another comet-like globule, located in the star-forming region known as CJ4 in the constellation Carina, 1,300 light-years away from us. The comet-like globule is named because its shape resembles that of a comet or a giant cosmic worm from Dune. A dense head formed of gas and dust, about 1.5 light-years in diameter, and an elongated faint tail about 8 light-years long, directed away from the supernova remnant. Inside are bright young stars, which apparently caused the destruction of the formation. And another interesting place in space is called NGC 281 or simply Pac-Man due to its shape, which is visible in wide-field images. The large cosmic head is located about 10,000 light-years away in the constellation Cassiopeia and includes a small open star cluster, a glowing reddish emission nebula, extensive dust regions, and dense gas dust formations. The next contender with an unusual shape is the open star cluster IC 1590 in the central region, which formed over the last few million years. The brightest star in this cluster is a multiple system. Its radiation ionizes the gas in the nebula, giving it a reddish glow. Dark Bok globules are well visible against the bright nebula. Sometimes you can see objects called Herbig-Haro objects emerging from the globules. These are small patches of nebulae associated with young stars. They form when gas ejected by these stars interacts with nearby clouds of gas and dust at speeds of several hundred kilometers per second. Herbig-Haro objects are characteristic of star-forming regions. Sometimes they are observed near single stars, elongated along the axis of rotation of the latter. These are temporary formations with a maximum lifespan of only a few thousand years. In images taken even with relatively short intervals, their high speed of penetration into interstellar gas clouds far from the parent star is noticeable. Some of the most captivating such objects are found in the famous Orion Nebula. In the photograph, obtained by combining 3 images at different wavelengths, the Waterfall Nebula or HH222 is visible as a yellow-green stripe descending from the upper left corner. It is located in the giant gas dust cloud of Orion, about 1,500 light-years away from us, and the waterfall stretches about 10 light-years. Yes, space is full of mysteries. The example with the donut appeared here for a reason. The fact is that maps of the cosmic microwave background, made using telescopes such as WMAP and Planck, showed an intriguing number of missing perturbations on large scales. This fun word means the deviation of a celestial body from its orbit under the influence of forces other than the gravitational attraction of the system's center of mass, such as other celestial bodies or medium resistance. To find out if these missing perturbations could be caused by a multiply-connected universe, many computer simulations were conducted to see what the cosmic microwave background would look like if the universe were a giant three-dimensional donut, where space is connected to itself in all 3 dimensions. Yes, the properties of observed fluctuations, that is, deviations from the average value of a random variable characterizing systems of a large number of chaotically interacting particles, of the cosmic microwave background show missing power on scales exceeding the size of the universe. Missing power means that fluctuations in the cosmic microwave background are not present on such scales and that our universe is indeed multiply-connected and finite. To put it simply, it seems that the cosmic microwave background lacks signals that should be there if the universe were truly infinite. One explanation for this suggests that the topology of the universe is curved in such a way that it connects back to itself, like a donut or bagel on intergalactic scales. Just as you can roll a sheet of paper into a tube without changing its parallel properties, the universe can have the shape of a donut while remaining flat. This is what researchers discovered through modeling the cosmic microwave background. Compared to the standard cosmological model, which is considered infinite, we have found a much better match to the observed fluctuations. Such a universe must have a limit, and the entire vast space may be only 4 times larger than the observable universe of humans. Its size is 47 billion light-years in diameter. The universe may be closed in 3 dimensions and actually have the shape of a 3-dimensional donut. Finite universe models can be frightening for some people, but you won't feel these boundaries. There won't be any claustrophobia either. Essentially, you just live in a boundless universe, even though it has a finite volume. But even if you don't necessarily reach the edge of this finite universe, can you circumnavigate it and return to where you started? Theoretically, yes, because light can travel throughout the finite universe. But it would take billions of years. It's interesting to imagine what our donut-shaped universe looks like from the outside, possibly lying in a state? The starry sky. It's something that always fascinates and makes you think about the infinite cosmos and our place in it. Looking at the night sky, we see a large number of stars. They are countless. There are too many of them. It seems that they are all very close to each other. But in reality, this is not the case. There is emptiness between them. The interstellar medium. For example, the distance to the nearest star from our Sun, Proxima Centauri, is just over 4 light-years. The distance to Sirius, the brightest star in the night sky in the northern hemisphere, is 8.5 light-years. These distances are enormous, aren't they? However, there are places in the universe where there is practically nothing. These cosmic formations are called voids, which in English means emptiness. It's hard to believe, but we live in one of these voids. Moreover, the largest void known to science. But let's take it step by step. As we know, matter is unevenly distributed in the universe. It forms a giant web, with filaments consisting of superclusters of galaxy clusters, which in turn consist of stars, gas, dust, and planets. Voids, on the other hand, are vast regions between the galactic filaments where galaxies and clusters are absent or almost absent. Their average sizes can range from 10 to 150 megaparsecs. To give you an idea, 1 parsec is equal to 3.26 light-years, which in turn is more than 200,000 astronomical units. And how many light-years does a relatively small void of 10 megaparsecs make? 32,615,000 light-years. Now let's try to convert this into kilometers. After such figures, it seems that your office isn't that far away, and you can calmly start walking, or simply embrace the futility. But let's delve into a bit of history. Cosmic voids became a subject of astrophysical study in the mid-1970s when astronomical surveys measuring redshift became more popular and allowed 2 independent groups of astrophysicists in 1978 to recognize superclusters and voids in the spatial distribution of galaxies. New surveys added depth to the 2-dimensional maps of cosmic structures, allowing the creation of the first 3-dimensional maps of the observable universe. In these surveys, the distance to galaxies was calculated from their redshift values, arising from the expansion of the universe. When sufficiently powerful telescopes and highly sensitive spectrometers, both ground-based and space-based, became available, the universe appeared to astronomers as a place where most matter is concentrated in galaxy clusters, and a vast part of space is occupied by voids, regions where the matter density is 15 to 50% lower than average. Shortly thereafter, astronomers from around the world gathered in Tallinn to exchange results of measurements of galaxy groups and their distribution in cosmic space. After this historic event, the concept of the large-scale structure of the universe gained its modern meaning. John Inasto, one of the pioneers in the study of large-scale structure, recalls how astronomical journals with the word "known" rejected his articles describing galactic filaments and the voids between them. Now, look at the computer simulation image of the millennium. The process of structure formation in a cube, 2 billion light-years in size, was simulated. For its first run in 2005, data from the WMAP mission, a NASA spacecraft that studied the cosmic microwave background radiation from the Big Bang, was used. After 2009, when the Planck Space Observatory refined the parameters of the cosmic microwave background, the simulation was repeatedly restarted. Each time, it took a month of work on the Planck Society's supercomputer. Eventually, the simulation showed the formation of galaxies, their distribution, the appearance of galaxy clusters, and the voids between them. The redistribution of dark matter, which began much earlier than the formation of the first galaxies, could only create superclusters and voids. In 2013, a group of astronomers concluded that the Milky Way, along with nearby galaxies, most of Laniakea, a supercluster of galaxies that includes the Virgo supercluster, of which the local group containing the Milky Way galaxy with our solar system is a part. And this entire structure is located in the midst of the truly gigantic largest void in the universe. The KBC void, named after astronomers Ryan, Ian, Emmy Barger, or Knox Cowie. As it turned out, this void is roughly spherical, about 2 billion light-years or 600 megaparsecs in diameter, with the Milky Way within a few hundred million light-years of its center. This is the largest supervoid known to science, significantly surpassing the size of the Eridanus supervoid and even the well-known large supervoid designated APLP-36, which is about 400 megaparsecs in size. For comparison, the size of our Milky Way galaxy is 0.3 megaparsecs. But even these seemingly empty intergalactic spaces are not as empty as astronomers once thought. Further observations of voids showed that the space they occupy still contains other components. The most common of these are protogalactic clouds. These are huge clouds of dust and gas from which galaxies subsequently form. But that's not all. It turned out that light from distant galaxies and stars passing through voids gets distorted. Researchers couldn't understand why this phenomenon occurs for a long time. It's known that light rays can be slightly distorted due to Earth's atmospheric movement, cosmic dust, or imperfections in telescope lenses. But how to explain such significant refraction? This remains a mystery to this day. A hypothetical answer is dark matter, which constitutes voids. In theoretical physics, dark matter is a form of matter that does not interact with electromagnetic forces and thus cannot be directly observed. It makes up about a quarter of the universe's mass energy and manifests only through gravitational interactions. Due to the lack of an electromagnetic field, observing and studying it, even with existing modern methods, is a daunting task. Nevertheless, using indirect theories, special mathematical calculations, and observations, astronomers suggest that such matter indeed exists. Back in 1987, Tully and Richard Fisher noticed that our galaxy, the Milky Way, lies on the edge of a vast cosmic void, which they called the local void. The idea of the local void was favorably received by scientists, yet this structure remains poorly understood because it lies in the direction of our galaxy's center and is difficult to observe. Despite this, the obtained results helped solve mysteries related to the expanding universe. Based on observations of galaxy movements, researchers determined the mass distribution explaining this movement and constructed 3D maps of the local void. Galaxy movement is linked not only to the universe's overall expansion but also to gravitational interactions between neighboring galaxies and high-mass regions. As a result, galaxies move away from denser areas towards less dense void zones. In their new work, Tully and his team measured movement parameters in 18,000 galaxies and created a cosmographic map, clearly showing boundaries between high-density zones and the local void. This method also helped identify the boundaries of our galaxy supercluster called Laniakea. Space indeed resembles a giant sponge, possibly wiping someone's table. Long, shining filaments of millions of galaxies alternate with voids, black gaps with far fewer star clusters. In truth, no one can see the universe this way. No matter where an observer is within the sponge, voids will seem like the inner surface of a sphere with the observer at its center. The universe remains full of mysteries, enigmas, and unsolved questions. The voice of cosmic voids. And in the future, more discoveries await us, which we will undoubtedly share with you. Everything beyond the observable universe remains a mystery and subject of endless debates and discussions among astrophysicists of all stripes. However, today we won't engage in an intellectual brawl, shouting random scientific terms. Instead, we'll try to simply explain what science has concluded about the universe's size and address one of the most pressing and complex questions about its nature. The first question that comes to mind for an average person is how the universe can be infinite. It seems undisputed that the container of everything around us should not have boundaries. If these boundaries do exist, what do they represent? Suppose someone you likely don't like flew to the edge of the universe, what would they see before them? A long-awaited dome, or maybe a fiery barrier with dragons, and what's beyond it? Emptiness, another universe, but can emptiness or another universe mean that we are beyond existence? Because that doesn't mean there's nothing there. Emptiness and another universe are still something, and the universe is everything. The visible size, also known as the Hubble radius, is 13.75 billion light-years. And the real size, known as the particle horizon, is 45.70 billion light-years. Essentially, neither of these horizons characterizes the actual size of the universe. First, they depend on the observer's position in space. Secondly, they change over time. In the case of the CDM model, the particle horizon expands faster than the Hubble horizon. Whether this trend will change in the future is a question modern science does not answer. But if we assume that the universe continues to expand at an accelerated pace, all the objects we see now will eventually disappear from our view. Let's look at this question practically, from small to large. The simplest method for determining distances in space is using light. However, considering how light spreads through space, we should understand that the objects we see from Earth may not look the same in space. It can take tens, hundreds, thousands, or even tens of thousands of years for light from distant objects to reach our planet. By then, humanity will be a bit worn out. Therefore, the simplest example of the difference between time and distances is sunlight. The average distance from us to the nearest star is about 150 million kilometers. Suppose you have a suitable telescope and this time protection for the second eye, allowing you to observe the sun. The point is, everything you see through the telescope actually happened on the sun 8 minutes ago. That's how long it takes for light to reach Earth. Light from Proxima Centauri will only reach us in 4 years. Or take a star like Betelgeuse, which stubbornly refuses to explode into a supernova. Even if that event happened now, we wouldn't know about it until the middle of the 27th century. Of course, a telescope is just one tool for measuring cosmic distances and isn't always able to handle the task. The farther an object is whose distance we want to measure, the harder it is to do so. Radio telescopes are excellent for measuring distances and conducting observations within our solar system. They can indeed provide very accurate data. But once you point them beyond the solar system, their efficiency drops dramatically. Due to all these problems, astronomers decided to use another method of measuring distance, parallax. What is parallax? Let's explain with a simple example. First, close one eye and look at an object, then close the other eye and look at the same object again. Did you notice a slight change in the object's position? This movement is called parallax, a method used to determine distances in space. The method works well when dealing with stars relatively close to us, within a radius of about 100 light-years. However, beyond this range, the method becomes less effective. The next way of determining distances is called the main sequence method. It's based on our knowledge of how stars of specific sizes change over time. First, the brightness and color of a star are determined, then compared with nearby stars with similar characteristics, using this data to derive an approximate distance. Again, this method is quite limited and only works for stars within our galaxy or those within a radius of 100 light-years. To look further, astronomers rely on the Cepheid variable method. It is based on the discovery by astronomer Henrietta Leavitt, who found a correlation between the period of a star's brightness variation and its luminosity. Thanks to this, many astronomers have been able to calculate distances to stars not only within our galaxy but also beyond. In some cases, these distances can reach 10 million light-years. Now we have an idea of the sizes and boundaries of the nearest galaxies, but we have not yet gotten any closer to the question of the universe's size. So we move on to the ultimate measuring tool. Fatality is based on the principle of redshift. The essence of redshift is similar to the Doppler effect. Think of a railroad crossing. Have you ever noticed how the sound of a train's horn changes depending on the distance, growing louder as it approaches and softer as it passes, leaving us momentarily stunned? Light works similarly. Look at a spectrogram. Do you see the black lines? They indicate the boundaries where elements within and around the light source absorb color. The more the lines are shifted towards the red part of the spectrum, the farther the object is from us. That's how we steadily approach our answer. Most light undergoing redshift belongs to galaxies around 13.8 billion years old. But consider one important detail. Throughout this time, since the so-called Big Bang, the universe has continued to expand like it's always New Year's Eve. In other words, this means the actual size of our universe is much larger than indicated in our initial measurements. It's important to note that these calculations are based only on what we can see ourselves, or more precisely, what we can discern in the depths of space. One way or another, it all points to the infinity of the universe, though it interprets this infinity very differently. Some believe the universe is multidimensional, where our local three-dimensional universe is just one of its layers. Others say the universe is fractal, meaning our local universe could be nested within another. Let's not forget the various multiverse models, with their closed, open, parallel universes and wormholes. And there are many, many different versions based on myths and legends, limited only by human imagination. But if we apply cold realism or simply distance ourselves from all these hypotheses, we might assume that our universe is an infinite, homogeneous container of all stars and galaxies. In any very distant point, whether billions of gigaparsecs away, all conditions will be exactly the same. In this point, there will be the same particle horizon and Hubble sphere with the same cosmic microwave background radiation and their edges. There will be similar stars and galaxies around. Interestingly, this does not contradict the universe's expansion. After all, it's not just the universe that expands, but its very space. The fact that at the moment of the Big Bang, the universe emerged from a single point only means that infinitely small, practically zero sizes that existed then have now turned into unimaginably large ones. Let's try to visually show the universe's size. Imagine our planet, the size of a buckwheat grain, which its inhabitants can't divide, orbiting around a watermelon, the Sun, the size of half a football field. In this case, Neptune's orbit would correspond to the size of a small city, the Oort cloud region to the Moon, and the Sun's gravitational boundary region to Mars. So, our solar system is as much larger than Earth as Mars is larger than a buckwheat grain, but that's only the beginning. Now imagine that this buckwheat grain is our system. Then the Milky Way would be the size of 2 football stadiums, but that still wouldn't be enough. We'd have to shrink the Milky Way to the size of a centimeter, resembling a coffee froth whirlpool in the midst of coffee-black intergalactic space. 20 centimeters from it lies a similar tiny spiral, the Andromeda Nebula. Around these cosmic cups will be a trio of small galaxies in our local cluster. Apparently, the size of our observable universe would be around 9 kilometers. Yes, this is how deeply humans can gaze into space. We understand cosmic sizes, but it's not enough to grasp the scale. It's important to comprehend the universe in dynamics. So let's imagine ourselves as giants, for whom the Milky Way has a centimeter diameter. As noted earlier, we'd find ourselves inside a sphere with a radius of nearly 10 kilometers. Imagine we can float like wizards inside the sphere, traveling at speeds of tens of light years per second. What would we see if our universe is infinite? Of course, we would encounter countless galaxies. In some areas, there'd be an abundance of them. In others, a void. The main feature would be that visually, they'd all be stationary. As long as we remain stationary, the moment we take a step, the galaxies themselves would move. For example, if we could observe the microscopic solar system within the centimeter-sized Milky Way, we could witness its development. Moving 600 meters away from our galaxy, we would see just the star Sun and the protoplanetary disk at the moment of formation. Approaching it, we would see the Earth forming, life emerging, and humans appearing. Similarly, we would see how species change and galaxies move as we move closer or farther from them. Therefore, the farther galaxies we observe, the older they will appear to us. The most distant galaxies will be located more than 1,300 meters away from us, and at the 1,380 meter mark, we will see the cosmic microwave background radiation. If we assume that the universe continues to expand at an accelerated pace, then being in the center of the bubble and fast-forwarding time by billions, trillions, and even higher orders of years, we will notice an even more interesting picture. Although our bubble will also increase in size, its changing components will move away from us even faster. Leaving the edge of this bubble, each particle of the universe will eventually wander in its own lonely bubble without the possibility of interacting with other particles. Currently, modern science does not have information about the actual size of the universe or whether it has boundaries. But we do know that the observable universe has a visible and true boundary called the Hubble radius and the particle horizon, respectively. These boundaries depend entirely on the observer's position in space and expand over time. If the Hubble radius expands strictly at the speed of light, the particle horizon expands at an accelerated rate. The question of whether the acceleration of the particle horizon will continue and not change remains open. And let's start our cosmic journey with the galaxy that is currently the closest to the Milky Way. This is the dwarf galaxy in the constellation Canis Major. It is only about 25,000 light-years away from the solar system. It is believed to contain 1 billion stars, many of which have already transitioned into the red giant phase, and it formed in the shape of an ellipse. Additionally, there is a whole stellar stream behind it. This complex ring-like structure is called the Monoceros ring. The ring appears as a chain of stars wrapped around the Milky Way 3 times. It is presumably a moving group of stars ejected by tidal forces from the dwarf galaxy in Canis Major, in the process of being absorbed by our galaxy. Among other members of the local group, two dwarf galaxies, satellites of the Milky Way, the Large and Small Magellanic Clouds, stand out with their mass and luminosity. These are large clouds of gas and stars, visible without the use of technology. However, they can only be seen from the southern hemisphere. They are 160,000 and 200,000 light-years away. Despite the short distance, their features were only identified in the last century. However, they still continue to hide mysteries. The Large Magellanic Cloud is located in the constellation Dorado. Because of this, it ranks third in proximity. The Small Magellanic Cloud resides in the constellation Tucana and holds the honorable fifth place in terms of proximity. Following from the names, the large cloud is twice the diameter of the small one. Its radius is 14,000 light-years. This makes it the fourth largest galaxy in the local group. It's possible that these galaxies could be passing clouds that were once stripped from Andromeda. The evidence of their interaction with our galaxy is shown by their altered structure and streams of neutral hydrogen. Their gravity also influenced the Milky Way, deforming its outer disk. These are the complex cosmic relationships. In reality, we are surrounded by dozens of different dwarf galaxies, but they all, to some extent, resemble each other. For example, the dwarf galaxy in Draco, the dwarf galaxy in the Sculptor constellation, the dwarf galaxy in Carina, the dwarf galaxy in Phoenix, the Barnard's galaxy, and dozens of other dwarf worlds. We simply don't have time to examine them all, so we move on to farther and larger objects. And the first to take this galactic baton is the third largest and most massive galaxy in the local group, as well as the closest spiral galaxy to the Milky Way without a bar. We're talking about M33, or the Triangulum galaxy in the constellation of the same name. It hosts a massive black hole X7, with a mass of approximately 16 solar masses. It is believed that the Triangulum galaxy contains about 40 billion stars, which is significantly less than the two other large galaxies in the local group. For example, the Milky Way is home to 400 billion stars, while the Andromeda galaxy contains a whole trillion. The Triangulum galaxy is currently moving towards Andromeda. These two galaxies have interacted in the past, as Andromeda's gravity pulled some stars from M33, and now this tail extends from one galaxy to the other. In fact, some of the Triangulum stars have migrated to the Andromeda galaxy. In the friendly company of galaxies, which span roughly 3 million light-years wide, besides the Milky Way and its satellites, we also have the Andromeda galaxy, the nearest giant spiral galaxy with a bar, and its satellites, which dominate the local group, located 2.5 million light-years away from us. It rightly holds a dominant position, being 1.5 times more massive than our galaxy, but we won't dwell on it more detailed because there's already a separate video fully dedicated to this world. Continuing our journey, we come across the galaxy NGC 5128, or Centaurus A, the nearest lenticular galaxy with a polar ring to the Milky Way in the Centaurus constellation. It's one of the brightest and closest neighboring galaxies. By brightness, this galaxy ranks fifth after the Magellanic Clouds, the Andromeda galaxy, and the Triangulum galaxy. This radio galaxy is a powerful source of radio emissions in the Centaurus constellation. And if we could see in the radio range, the intense emissions from the galaxy would be visible as two huge formations emanating from the galaxy's center. Centaurus A spans 60,000 light-years in diameter. Such stellar formations typically lack arms, and the bright central cluster is highly compressed, resembling a lens. It consists mainly of old stars, giving it a reddish hue. Before us is the irregular galaxy Wolf-Lund-Markmelot, discovered in 1909 by Max Wolf. It is located in the constellation Cetus at the edge of the local group. The distance is approximately 3 million light-years. It experiences tidal interactions from another local group member, the dwarf elliptical galaxy JC-29-194. In the southern hemisphere's night sky, 175,000 light-years away from us in the constellation Dorado, lies an object of truly colossal size. The emission nebula N.J/2070, better known as the Tarantula Nebula. This nebula is considered a giant and the largest known nebula to date. This nebula is one of the brightest cosmic objects observed from Earth. Today, there isn't an astronomer who hasn't heard of this cosmic wonder. It is now known that the Tarantula Nebula is a star-forming region. Previously, due to the lack of powerful observational equipment, it was thought to be just one of the brightest stars in the night sky from the constellation Dorado. Nicolas Louis de Lacaille first recognized its true nature in 1751. Later observations with modern telescopes showed that this cosmic object is not a star but a nebula where stars are born. This cosmic object is enormous. Just imagine, the diameter of this nebula is about 1,000 light-years. If we swapped it with the Orion Nebula, the nearest similar object to us, it would cover a third of the night sky. Its size would exceed the familiar moon by 60 times. Such a night sky view would be mesmerizing. This nebula belongs to the Milky Way's satellite galaxy, the Large Magellanic Cloud. It is an extensive emission region of ionized hydrogen where new stars form. The sources of ionizing photons are young massive stars. The huge stars in the nebula are also powerful sources of radiation, blowing giant cosmic bubbles out of interstellar gas and dust. This is quite a curious phenomenon. These objects form through the gravitational influence of large stars in the nebula on the gas clusters within it. Under this influence, gases are blown out, forming shapes that visually resemble bubbles. Some of the stars have exploded as supernovae, illuminating the bubbles with X-ray radiation. This is why the Tarantula Nebula is so bright, allowing us to observe it with the naked eye. However, to do so, you need to travel to the southern hemisphere. And to see the precise contours of this cosmic object and discern some of its larger details, it's best to bring a good home or semi-professional telescope. And the VLT Survey telescope at the European Southern Observatory in Chile managed to capture this nebula, its rich star population in very fine and precise details. For example, you can see a cosmic landscape of various star clusters, hot gas clouds, and remnants of supernova explosions. The Tarantula Nebula got its name because it resembles the venomous spider, the tarantula. Its central part, similar to the spider's body, is home to massive and bright stars. The spider's legs are gas clusters, primarily hydrogen. The nebula is literally teeming with this chemical element. But this giant spider is actually benign. The tarantula's legs embrace one of the largest known cosmic objects, the star cluster NGC 2070, which is an active star-forming region with its dense core, R136, containing some of the largest and brightest stars. With the unique ability of the Hubble Space Telescope to capture ultraviolet radiation, researchers identified 9 monster stars in the R136 cluster, each with masses exceeding 100 solar masses. This makes the R136 cluster the largest known collection of massive stars to date. Initially, it was known that the cluster contained many stars with masses 50 times greater than the Sun. The new research showed that R136 houses at least 9 stars with masses exceeding 100 solar masses. Among them is the current mass record holder, the star R136A1, which is 250 times the mass of the Sun and is rightfully considered the heaviest star in the known universe. The discovered stars are not only extremely massive but also quite bright, approximately 30 million times the luminosity of the Sun. Astronomers also studied the outflows from these monster stars in the ultraviolet range. Each month, they eject a mass comparable to Earth's mass at speeds of about 1% of the speed of light. It's believed that such outflows lead to an extremely rapid loss of mass. Astronomers are still trying to explain the origin of such giant stars. There are even hypotheses that these giant stars might have formed through the merger of less massive stars in tight binary systems. Another interesting star cluster in this nebula is Hodge 301, where at least 40 stars have already exploded as supernovae, spreading their gas shells throughout the region. One example of a supernova remnant is the superbubble SNRN 157b, which contains the open star cluster NGC 2060. This cluster was discovered by British astronomer John Herschel in 1836 at the Cape of Good Hope in South Africa using an 18-inch reflector telescope. In the lower right region of the Tarantula Nebula, you can identify the well-known supernova SN 1987A. This supernova was the first to be observed with modern telescopes and the brightest since Kepler's star explosion in 1604. The brightness of SN 1987A was so intense that for several months after its discovery in 1987, it emitted at 100 million suns power. And if you look to the left of this nebula, you can see another open star cluster called NGC 2100, which shows us a collection of blue stars surrounded by red ones. This group was discovered by Scottish astronomer James Dunlop in 1826 during his work in Australia with a 23 centimeters reflector. Also located in the nebula is the Star Cluster and Emission Nebula NGC 2074, another large star-forming region. If you look closely, you can see a dark, dusty structure in the shape of a seahorse. This feature is called the Seahorse in the Large Magellanic Cloud. In reality, this is a giant pillar-like structure about 20 light-years long, nearly 5 times the distance between our Sun and the nearest star, Alpha Centauri. This cosmic seahorse is expected to disappear completely within the next million years as the star cluster continues to form new stars, whose radiation and winds will slowly disperse these structures. Yes, the Tarantula Nebula is unique, enormous, and contains many fascinating objects. It serves as a cradle for the birth of new stars, while other stars end their lives by exploding as supernovae. It is a true treasure trove of information and invaluable data for astronomers who still have many questions to answer. And there you have it, folks. The cosmic journey through the vast universe has been nothing short of mesmerizing. We've explored dwarf galaxies, encountered breathtaking nebulae like the Tarantula, and marveled at the colossal structures that form our universe. If you enjoyed this exploration and want to dive deeper into the mysteries of the cosmos, make sure to hit that like button and subscribe to the Curiosity Dude channel. Stay curious and keep looking up.